In vapor power cycles, we had a number of ways to improve the efficiency. The TS diagram is really helpful to explain why that scheme should help improve efficiency from an entropy transfer point of view. So we talked about superheating already, and reheat we'll talk about already, where you take the steam back for an extra pass to reheat it. So it gets heated once through the main pass, goes through a turbine, it's lower pressure, reheat it, then back to another pressure turbine. On a temperature entropy diagram, what you're doing is trying to bring in more heat at this high temperature region. The other is with an open feed water heater. We want to somehow get the fluid that comes into that steam generator, into that boiler that's going to be heated up right in here. We want the temperature at 8 to be high. We don't want to use expensive fuel like coal to heat it up when it's still a liquid. We really would like to just get it up to change phase, boil it, superheat it. Okay, so one strategy for doing that is using a feed water heater. There's two types. We'll talk first about an open feed water heater. In an open feed water heater, you have two inlet streams. Here's an inlet and one outlet. And they just mix. It's just a box where you don't, two pipes come into the box, mix, and it goes out in a third pipe. This pressure at 6 and the pressure at 2 and the pressure at 7 are all the same pressure. Remember, in our ideal system, even though you have pipes and you have flow through the pipe, we neglect the pressure drop in the pipe. We have pressure gains and drops. Gains in pumps, drops in turbines, and that's it. Is there a pressure drop through the condenser from 4 to 5? No. You neglect it. It's neglected. Okay, so how much fluid do we divert down? Well, we introduce a symbol Y. And Y is a ratio of mass flow rates. It's the mass flow rate that's coming down to feed the open feed water heater that's diverted after the first turbine stage. That's how much comes down to it from there. And then it's divided by the mass flow rate that goes into the first turbine stage. You say, well, that kind of seems a little odd to name it that way. But no, it's not that odd, and it's very helpful. So I sometimes will talk about what goes through the first pass of the boiler or first pass of a steam generator. I can use that terminology as well. I'll try to stay with what the textbook, which talks about what goes into the first turbine stage. So that's our fraction. If we do a mass balance, take a look. Just chase through your mass flow rates. So you have the mass flow rate into the first turbine stage, the mass flow rate going down to the open feed water heater. What about that goes back for reheat? Well, isn't that the mass flow rate that went into the first turbine stage minus the mass flow rate that went down to the open feed water heater from a mass balance? How about that goes into the second turbine stage? Isn't that the mass flow rate that went to the reheat, which is the same as the mass flow rate to the first turbine stage minus what went down to the open feed water heater? How about through the condenser, into the condenser? So these mass flow rates through the second turbine stage, through the condenser, through the first pump, are all the same mass flow rates. That's it. That's the only time it splits. And where does it join? Where does it join back together? Open feed water heater. So you have a split, then you have two separate paths. One path that's really short. It just goes from here down. The other path goes all the way, all the way, all the way, all the way. Then finally they join back up. So a lot of times they'll use this notation. Y is that fraction that went into the first turbine stage that was diverted. 1 minus Y is the fraction that continued for reheat, second turbine stage, condenser, pump, and then finally back into the open feed water heater. So I know I messed this up a lot, but you can put it in, not in terms of mass flow rates, but you can put it in terms of percentages. 100% comes in the first turbine stage. Y percent goes down. 1 minus Y continues to reheat. over to 1 minus y into the second turbine stage, 1 minus y in through the condenser, 1 minus y out of the condenser into the first pump, 1 minus y out of the first pump into the open feed water heater. And then what comes out? 100% again. And then it's back to 100% and 100%. So use those, the y's, the 1 minus y's, and 100% to get the mass flow rates. Now, if you do an energy balance around that open feed water heater, you'll get the equation for y. That's how you determine how much is diverted. Because what do we want out? Think about making pump 2 happy. You want to make pump 2 happy? How do you make pump 2 happy? What do you feed it? You feed it superheated vapor? No. Do you want to feed it some two-phase quality? No. What would you like to feed the pump? Saturated liquids. So state 7 is saturated liquid. If you take a look over here, state 7 is, you could kind of tell by this temperature, and it's saturated liquid, okay? So state 7 is saturated liquid. So anyway, if I do an energy balance, what does the energy balance equation look like? Well, what am I bringing in? Let me kind of write it out in detail here. The mass flow rate times the enthalpy that it's coming with enthalpy 2. And the mass flow rate that's, how do I say it, is the turbine 1 minus the mass flow rate open feed water heater. Isn't that the mass flow rate that went through the second turbine stage, went through the condenser, went through the first pump, times the enthalpy that it brings, H6, then the outlet flow rate, well, that's back to the m dot T1, what goes into the first turbine stage, times the enthalpy at 7. That's a subscript 7. And you kind of look, you say, I know that one. And if I could get H6 and H2, then great. I think I could get an equation for y. So you divide the whole equation by m dot turbine 1, m dot turbine 1, m dot turbine 1. Maybe I should put it like this. Divide. M dot turbine 1. So the equation, the energy balance is y times H2 plus 1 minus y times H6 is equal to 1 times H7. Thumbs up. You like that? Then I could solve for y, and it looks like it's H7 minus H6 divided by H2 minus H6. But don't memorize that equation, because the subscripts may change. Oh, it's now state 2 on the old diagram and state 4 on the new diagram. You should be able to rederive. How did we do it? Energy balance. Here, take a look at the enthalpy state 2. It's quite high, isn't it? It's a lot. So the reason it's a lot is most of it's vapor. And when it comes in, it's going to condense. And when it condenses, it boosts the pressure of that cold liquid coming from the pump. So it comes out hot. The mixture comes out hot. Take a look at the temperature at 6. The temperature at 6 is 60 degrees. What's the temperature at 7 coming out? 180. Oh, there must be a heater in here. Is there a heater in there? How could the temperature go up from 60 to 100 and almost 80? You mixed hot steam in. State 2, look at the temperature. I know it's only 180, but you brought in, all that vapor brought up the whole mixture to be saturated liquid. Yep, no heater needed, was it? No heater. It's just mixing. But it's 100% liquid. It's all liquid coming out. All right. Once you get that down, then you got the Y's. I already encouraged you last time. March through the pressures. Make sure you know the pressures at each state through the cycle. Now make sure you know the mass fractions going through the cycle. Sometimes it's not so easy. You have to work at it. You want to calculate something like the thermal efficiency. True? and the back work ratio for this cycle. Let me do this. I'm going to show you a common error and then show you how to avoid that common error. Is if I want to calculate the thermal efficiency, the thermal efficiency is the net work out of the cycle divided by the heat that comes into the cycle. Okay? Let's do heat into the cycle first, Q in. I have one place from 8 to 1. And then I have another place 2 to 3. Can you see that? I know 2 is all here, and then 3 goes out. So 2 and 3. So let's get the heat that comes in 1 to 8, or the first pass, pass 1. And then we'll add to it Q of the second pass, the reheat pass, okay? So what is this lowercase q pass 1? Is it H1 minus H8? How many kilojoules of heat per kilogram of the water or steam that went through that first pass? Isn't that the units? Kilojoules per kilogram. But I emphasize, it's per kilogram that went through that first pass. Now let's do minus the second pass. Is that going to be H3 minus H2? Yeah, but it's kilojoules per kilogram that goes through the second pass. This was per kilogram that went through the first pass. Are these kilograms the same? Nope. So if I have 1 kilogram going through the first pass, I may only have 0.8 kilograms going through the second pass. For every 1 kilogram through the first pass, I may only have 0.8 kilograms being reheated. True? So there's a couple ways of doing this, but do this. Do Q dot in, which is the mass flow rate that goes into the first turbine stage, times H1 minus H8 plus the mass flow rate that goes through the second turbine stage. Well, what was that mass flow rate? Wasn't that what went through the first turbine stage minus what went down to the open feed water heater? And then multiply that by H3 minus H2, kind of cramming it in there, but I'm going to wait, let your mind process that until you give me a thumbs up that you agree. Do you agree? Do you see what I did? All right, I start with the front row. You're still looking. Don't let me force you. Does you agree or not? Kind of, yeah. How about second row? Everybody here, are you on board? Yeah, what we have is we want the total amount of heat into the working fluid in the boiler. It's like this is the coming into the cycle, Q dot. This is not kilojoules per kilogram, this is kilowatts. And it's coming in here and there. And so this is the mass flow rate through the first pass times the enthalpy change of that fluid going through the first pass. This is the mass flow rate going through the second pass times the enthalpy change of the fluid in the second pass. Does that help? I sum them up. I have total Q dot in. True? Now if I divide this by, what do you think I want to divide it by? M dot T1, exactly. M dot T1 minus M dot, well, this is, just put it all over M dot T1. And what you get is you get lowercase q in is equal to 1 times H1 minus H8 plus, now what is that ratio there? 1, well, come on, write 1. 1 minus Y times H3 minus H2. Agree? So what was missing on this equation right here, which was, I knew there would be an error, is I didn't put the 1 minus Y. But if you just look at why did that 1 minus Y show up, go back to Q dot and do it slowly from there. Do you agree? Looks good? So now what we've done is we've said this part of heat in and that part of heat in are all on the same per kilogram basis. Everything's per kilogram going into the first turbine stage. Once you have Q in, you're almost ready to calculate the efficiency. What do you have to do is the net work, W net, right? I'm going to have some work out of the first turbine, some work out of the second turbine, some work into the first pump, some work into the second pump. I have 4 things to keep track of, right? So let me do this. I'll just try and do it this way. I'll scroll up. The work net in. I can do it in 2 steps. This is a lowercase w. I could go with a cap W dub like that. Should I do it that way and then divide by m dot T1 to show you? Okay. So this will be the mass flow rate through that first turbine stage times H for the first turbine, H1 minus H2. Then we have a positive out mass flow rate that goes to the second turbine, but that's m dot T1 minus m dot open feed water heater. So that's the mass flow rate that goes through that second turbine stage times H3 minus H4. Those are my 2 positive workouts from the 2 turbines. It's power out. True? Minus the mass flow rate that goes through the first pump. You know what? That's still, isn't that true? Times H6 minus H5. If you're thinking, what is H6 minus H5? It's VDP. VDP, true. It's a good approximation of the work. Minus the mass flow rate that goes through the second pump, which is the same as the mass flow rate that goes into the first turbine stage. What goes through the second pump goes into the first turbine stage, true? And that's times H8 minus H7. Now that we have it on a power or m dot, q dot, or not q dot, w dot power basis, what do we divide that equation by? M dot T1. And when you divide it by m dot T1, this becomes lowercase w net. This becomes H1 minus H2 times 100% plus 1 minus y. That's a bad looking y, but there it is. H3 minus H4 minus 1 minus y times H6 minus H5 minus 100% times H8 minus H7. Agree or disagree? Good. Looks good? All right. Well, there, I think that's the hardest part. And how about the back work ratio? I could tuck it in maybe right here. The back work ratio is going to be the sum of the 1 minus y times H6 minus H5. That's to work the first pump, plus H8 minus H9, the second pump. And you divide it by what the first turbine came out with, H1 minus H2. And the second turbine, 1 minus y times, that's a plus there, H3 minus H4, the back work ratio. Do you agree? This is 8 right there, minus 7, right? Yeah, sorry about that. H8 minus H7 for the second pump. Yes, thank you. Can we sketch that one on a TS diagram? Whereas state 1, it was around 10 megapascal, if my memory is correct, around 440, 450. It's up here. About that temperature, that pressure, boom, superheated vapor. You pass it through a reversible turbine, maybe you come down to 2 megapascal, or was it 1 megapascal? Somewhere you're going to bring it down here. You can see if you go to lower pressures after the first turbine stage, you're getting lower quality steam. So somewhere you stop. Okay, we stop here for state 2, and then we put it through the reheat, took it out to the 440 again. There's state 3. Then we pass it through the second turbine stage, and maybe we stopped at 20 kilopascal. There's state 4. Well, it's low pressure, high quality steam, but you have to condense it in the condenser. There's state 5. State 6, it's right there. It's right on top of it. Hard to show them separated by any distance on a TS diagram, but there it is, because that's after that first pump. But now, I need to remind you, after that first pump, state 2 and state 6 mixed to give state 7. And state 7 was saturated liquid at what pressure? Well, the pressure at 7, same as pressure at 6, same as pressure at 2, right? So, where is state 7? And I know a lot of people will get this wrong on a TS diagram, so what I'm going to do is I'm going to pause and let you just quickly sketch where is state 7 on a TS diagram. All right, whenever you're asked a question like that, locate a state on a TS diagram, and especially on these power cycles, how many lines of constant pressure or different unique pressures do we have in our system? We have 3 of them. You probably want to sketch, let's say, a 10 megapascal line of constant pressure isobar. You probably want to sketch a line of constant 2 megapascal, and then you want to sketch a line of 20 kilopascal. And then if you know state 7 is that pressure, don't place it on the wrong line. Got to be on that line, right? So your pressures will keep. A lot of people put 7, like this is right here. Maybe they put 7 up here. No, don't do that. Right? 7 is 2 megapascal saturated liquid. So right there is state 7. Okay, then the next one is, where's 8? 8 is right after that pump. Okay, it boosted it up to 10 megapascal. So some people will put 8 right up here. What do you think? No. No. It's right there. That's where 8 is. True? Just like 6 is a little bit above 5 on a TS diagram. And I mean a little bit above. Maybe a degree above, half a degree above. Is 5 saturated liquid? 5 is saturated liquid, 6 is subcooled or compressed liquid. That's right. 7 is back to saturated liquid. So there you go. Sure. So 7 is saturated liquid, 5 is saturated liquid coming out of the condenser. What you want to feed into the pump. Yeah. Some of these percentages don't make sense. I should have deleted them. Probably should have deleted this and deleted that. But this is saturated liquid. They just happen to be the same quality. If you expand it down to 1 megapascal, yeah, this is 1 megapascal, isn't it? You get the same quality as if you expand, then reheated down to 20 kilopascal. So all this time I should have been on this line, should have gone down here to 2. And then reheat and expand, and 4 is over there. Hey, look at that. There it was. The answer was on the next, but that's what it looks like, right? Go now with a closed feed water heater. Now the open, it just mixes. Closed, it's helpful to think of tubes and shell. So I have a shell like this, and then I bring in an inlet pipe and an outlet pipe, and I have a plate right here, and all of this is open on this side so that the flow can come in and seek out one of the holes that goes to different tubes that run through the shell. That makes sense? And then there's a plate down here, and then all the tubes can empty out and collect up and go out the other end. So the flow of one fluid is through the tubes, and the other fluid maybe come like this and go out that way. It goes through the shell side. And depending what you have, you could make baffles here so that the flow is forced to cross the tubes repeatedly. If it's a gas-gas heat exchanger, something like that, or liquid-liquid heat exchanger. But here, if you're just going to condense it, it's not that important to have baffles. What you have, though, is you bring in this fluid from state 2. What is the condition of the fluid coming from state 2? It's not quite superheated. Let's say it's a high-quality steam. There's a lot of ability to condense, and when it condenses, it transfers heat. Right? It's hot steam, high quality, maybe 96%, 95%. It could be superheated, but probably not. And then what do you think you'd like to come out the bottom of it? It's going to condense on the shells, on the shell side. A liquid will collect in the bottom in the fluence of gravity. And what do you think they take out? Saturated liquid. What do you think the difference in pressure is between state 2 and state 7? The pressure at 7 is equal to the pressure at 2. There's no difference. We neglect the resistance to flow around the tubes. Okay. Now, inside the tubes, it comes in at state 5, and it goes out at state 6. The pressure's been boosted in the pump. What is the condition of the fluid at state 5? What is it? Saturated liquid, superheated vapor, subcooled, two-phase? Right, compressed or subcooled liquid, right? And then what would you like out at 6? You would like it as hot as you can get it. And you're not feeding it into a pump, so it doesn't have to be saturated liquid. But what's the pressure at 6 compared to the pressure at 5? The pressure is going to be higher or the same pressure? Same pressure. Hey, what is the pressure at 1 versus the pressure at 6? You know what? It's a high, high, high pressure coming out of those, out on the tube side of that closed feed water heater. Very high pressure, right? Okay. This allows you to condense maybe at a high temperature and to bring this out right here. Don't think any more saturated liquid at state 6. It's still subcooled liquid. Can the temperature at 6 be greater than the temperature at 2, assuming 2 is some two-phase, steam? No. It's just a heat exchanger. Heat's always going to go from something hot to something cold. The fluid inside the tubes are cold. The steam that's condensing on the outside is hot, and it's transferring heat to the tubes. As it transfers heat to the tube, the steam condenses, it collects, drips to the bottom. The temperature at 6 has to be less than typically the saturation temperature at that pressure of the steam on the outside of the tubes. Now, what are you going to do with this liquid? There's a couple things you can do with the liquid. You could put that into a pump and then blow it back up. That's one thing you could do, where this would just be a mixing right here. Or what we've shown here is you take that liquid and put it through what they call a steam trap. And then it's at state 8, and it's fed into the condenser. Now, let me ask a question. The pressure at 3 versus the pressure at 4. The pressure at 3 and the pressure at 4, are they the same pressure? How about the pressure at 8 versus the pressure at 3 and the pressure at 4? Are all three of those the same pressure? They're all the same pressure. That's the low pressure. That's the condenser pressure. So guess what the steam trap does? It has a significant pressure drop across it. There's a significant pressure. That's sometimes why they put the little X in here. It looks like a restriction. Okay? Now, there are a lot of steam traps. There are a couple different designs on them. They're clever, ingenious engineering devices. You can go out to the internet. You can look at videos that last 37 minutes on steam traps and all the designs. And they're just incredible devices, and they show you how they work, etc. Okay? But guess what? I don't have 37 minutes of class time to show you all about steam traps. So I'm going to skip this. There's all kinds of very good engineering videos that explain these devices. But let me try my 2-minute explanation on a steam trap, okay? If I can now stop this. It's a police officer with his big hand up saying, stop. What's he saying stop to? The flow of vapor. And as soon as enough liquid piles up, he says, okay, I got 10 cars of liquid piled up. Now you can come. And then obviously you're the 11th car. Stop. Then you got to wait until more cars come. But he's never going to let any vapor through. That's what it is. That's a device. It's just a device that says no vapor goes, but liquid condensate can. Now, they also unfortunately have problems with real systems having non-condensables, air, carbon dioxide, nitrogen in steam systems. You don't want that in the steam system. You want pure water, H2O, in there. So they're very clever. They'll actually blow out non-condensable gases as well. And a lot of times they'll let the little bit of liquid just drip out, go somewhere, or the gases will blow out to the atmosphere, or sometimes they're designed such they drop back into a return loop, and so then the condensate goes back to the boiler, and any non-condensables vent to the atmosphere in the plant. Okay, that was a lot of engineering explained in less than 2 minutes. Okay, now what is state 8? Is state 8 saturated liquid? The pressure dropped. Can you do an energy balance around the steam trap? If you do an energy balance around the steam trap, what two properties help fix state 8? What two properties? Pressure and, make the list. You say pressure, temperature, specific volume, internal energy, enthalpy, entropy. We got a couple votes for enthalpy. Is the person saying enthalpy correct? Is it pressure and enthalpy that fix the state 8? All it is an energy balance around the steam trap, a particular type of restriction that is so good that it knows when to not let any more. A lot of these steam traps operate not continuously but episodically. Does that make sense? Pressure and enthalpy fix state 8. What is the enthalpy at 8? We don't have time to sketch this, but I want to sketch it on a temperature entropy diagram, okay? And what you're doing is you're getting the fluid in this region, which is low temperature, heated without getting that heat from coal. You're getting that heat from inside the cycle, and so that boosts the efficiency of the overall cycle. Thank you for your attention.